This is Chemical Processes for Micro and Nano Fabrication. I'm Chris Mack, and this is Lecture 32, Semiconductor Manufacturing. In particular, we're going to talk about yield and defects. Yield is obviously a very critical part of the whole idea of manufacturing a chip, because we're not manufacturing for the fun of it, we're manufacturing to sell. And what is the yield? Well, yield is the fraction of the product that we start to make that we can actually sell. Unfortunately, not every chip that we make actually works, and we need a way of expressing and describing this fraction of chips that work numerically. A standard of quality control, a standard idea of quality control is you can only improve what you can measure. You can only improve what you can put a numerical value on. And yield is our overall measure of the quality of our manufacturing process. What's involved in that? We describe different parts of the process with different yield metrics. First of all, there's a wafer yield. So we have what are called wafer starts. This is when we take a blank, bare wafer and begin the process of manufacturing with it. A wafer fab might have 10,000 wafer starts a week, or 5,000 wafer starts a week, or something like that. But through the course of manufacturing, not every one of those wafers survives. Some of them are scrapped. They might be scrapped because we drop it on the floor and it shatters. But more than likely it's scrapped because some misprocessing occurs, and we know that every single die on that wafer is dead. There's no way it could possibly work after some mistake was made. So those are scrapped wafers. And the wafer yield will be the wafer starts minus the wafers scrapped divided by the wafer starts, or the fraction of the wafers that we start that we actually end up with at the end. Now, of the wafers at the end, we talk about the die yield. So we test the die and we ask how many good die are there per wafer. Of course, we only test the wafers that aren't scrapped, so die yield is in addition to wafer yield. Die yield is one of the more important metrics that we think about in the fab, but we don't make die, we make finished packaged chips. So we also worry about things like assembly yield. That means assembling the die into a package. And some of those don't survive the ordeal of being packaged, and good die might actually go bad. And finally, there's something called the burn-in yield. After we've finished packaging a device, we test it. The die was working fine, but the tested device might still work fine, but we need to run it for a little while. It's called burn-in. We actually let it operate for a short while because of the problem of infant mortality. A device that works after you test it runs for a couple of days or a couple of hours, and then it dies because there's some lingering defect that only after a little bit of operation will we find out. So we don't want to ship chips to our customers that die within the first hour of being used, so we do this burn-in test. And so there's a burn-in yield. And finally, the overall yield will be the product of each of these individual yield values. Our goal is, of course, to make the yield higher. So what affects yield? We call this yield loss. Yield loss comes from two basic sources: parametric yield loss and defects. Parametric yield loss means errors in things that we can put a numerical value on. Errors in the thickness of the film that we've deposited. Errors in the feature size of the pattern that we've created. Errors in doping concentration. Errors in etch depth. All the different process steps where we're trying to achieve a certain target. If the actual deviates from that target in too great a way, we call this a parametric error. And if those parametric errors are too big, then we could have a device that doesn't work. Parametric yield loss is a major source of yield loss whenever we're pushing the forefront of our processes to the next level. Usually once a process has matured, we've ensured that the parametric yield losses remain small. But for brand new processes, this is often a big source of yield loss. And then separate from this parametric yield losses is defects. Of course, we can measure the number of defects we have. We can measure the size of the defects, but they're not really parameters per se. Our goal is to have no defects. Defects are more random in nature. They come and go. There's no, sometimes there's systematic cases, but even for systematic sources of defects, the positions and such for these defects tend to be random in nature. And they cause yield loss. If they're big enough and they land in the right spot, they can kill a device. Defects usually are very high. The levels of defects are usually very high when we begin a new process. And we quickly learn. It's called yield learning. We figure out where the defects are coming from. We go and address those issues, and we eliminate them. And very quickly, at least we hope very quickly, our defect densities go way down and our yield goes way up. We call this yield learning, and it's a natural part of the startup of any new process. Defects are historically been the #1 killer of yields, although today it's more even between how defects kill the yield versus how parametric errors cause yield loss. But defects are any kind of, it's dirt, right? It's particles, contamination, even things like scratches and defects in the crystals, impurities in the chemicals that we apply to the wafer, even things like electrostatic discharge. This is in the fab. The actual handling of the wafer can cause static shocks to the chips, and even before we're done processing the wafers, we might kill some chips due to electrostatic discharge. The way you deal with defects is to try to eliminate the sources. So, depending on where the defect comes from, we'll have different strategies for reducing those defects. So, for example, defects from the environment, from the air around us. Well, how do we deal with that? First thing we do is we use clean rooms. We use a room with HEPA filtered air, and all of the people wear these bunny suits that completely cover them up to protect them, actually to protect the wafers from the people, from the dirt that people generate. And then we go around looking for all the sources of defects and try to eliminate them. Additionally, there can be particles in the process chemicals. So what do? We purify those process chemicals. Before we apply them to a wafer, we also filter them. And we can use a point of use filtration, where just before the chemical is to be applied to the wafer, we have a filter to try to get rid of any defects that might be there. Handling errors. These wafers get moved around from point A to point B, in and out of carriers. In the old days, people would grab wafers with tweezers and move them from place to place. Today, it's almost all automated systems. And so the automation helps to reduce these handling errors. That doesn't mean there is none, though, because even with automation, these robots can generate defects and generate static electricity, so that needs to be controlled. And then finally, there's equipment-induced defects. You put a wafer into an implant machine, and maybe there's some moving parts that generate particles that come and land on the wafer. Certainly in a CVD equipment, if we don't clean the tubes frequently enough, we can get particles that can land on the wafers. So what we do is monitor the wafers using defect detection and review capabilities, and then eliminate the sources. Make sure the equipment begins clean and stays clean as it's operating on the wafers. To understand what level of defect is significant, we use a defect model. the basic defect model, the simplest one, and there's a lot more complicated ones than just this one, but this is the simple basic defect model. It assumes all of the defects are independent of each other, and the yield, y, is a function of three things. First of all, we have what's labeled here as G, the fraction of die that always fail. Now, there are some die that come all the way out to the edge of the wafer, and they just don't work. They're too close to the edge, they're too close to the portion of the wafer where everything is non-uniform, and those die always fail. Now, we work very hard to make G as small a number as possible. We want all the die to work, even the ones that go all the way out to the edge. But nonetheless, there is a certain number of die which don't really have anything to do with defects. They're just dying, they're going to fail because they're out at the edge. So ignoring those, so we do 1 minus G, ignoring those die, then there's two parameters that we worry about. First is the critical area, A sub C. This is the area of the die where a defect matters. So there are some areas of the die that are just kind of open space or space with non-critical features on it. And if a defect lands there, it just doesn't do anything. Especially the small defects. I'll talk about defect size in a minute, but if we have some area where the defect doesn't matter, we simply don't worry about that. Instead, we count up all the area that is critical. This is if a defect lands there, it's going to kill the die. And then D0 is our defect density. This is the density number of killer defects per unit area. Now, I say the number of killer defects because depending on the process technology, there's a certain kind of defect size that matters. If a defect gets too small, it stops being a worry. It stops causing device failure. And then once it reaches a certain size, at that size and larger, it'll always kill a device when it lands in the critical area. And that's important to know because there are always more small defects than big defects. We're pretty good at eliminating big chunks of dirt floating around in the atmosphere and such. But the smaller the defect gets, the harder it is to filter it out, to eliminate it, and keep it away from our wafer. So when we say defect density, we always have to specify what size of defect that we're talking about. In reality, though, defects often cluster together. They don't actually act independently. And so the yield that we predict with this independent equation is usually low. You can only kill a die once. So if you get a cluster of 3 defects and they're all on the same die, well, it didn't cause 3 failures, didn't cause 3 dies to fail. It only caused 1 die to fail because they were clustered together. So clustering actually reduces the impact of the defects. And we have more significant, more complex models that take this clustering into effect as well, but we're not going to cover that here. The important thing to know about this equation is that there's going to be 2 ways in which we can improve the yield based on defects. One is we can reduce the defect density. This is kind of the obvious thing, get rid of the defects. But the other thing is we can reduce the critical area of the die, and we'll talk about that later. So how do we reduce defect yield loss? Well, I guess later is right now. We'll reduce the critical area. This is something called design for manufacturability. We look at our design and say, is there any way we can tweak this design so that it's less sensitive to a defect? One of the examples is wire spreading. Suppose I have a whole bunch of wires and they're very dense, but I have some open space next to it. I could spread the wires out. A defect that comes and lands and crosses 2 wires will cause a short circuit. But if I spread those out, that same size defect won't be able to cause a short circuit. And therefore, once these wires are spread far enough apart from each other, they no longer become part of the critical area. Redundant vias. If I'm making a via to connect one layer of metal to another, if a defect lands on that via, boom, it's dead. One dead via, it means an entire chip is dead. But if I have room I might be able to overlap the two lines a little bit more and put two vias connecting one level of metal line to another level of metal line. That's called a redundant via. If a defect lands on one of them, it doesn't do anything because I have a backup. The probability of getting two defects, one landing on each via, becomes very, very small. So I can dramatically reduce the critical area if I have room on the chip to put redundant vias. Not every chip allows that, but if I can, that will be very valuable. This idea of changing the design to make it yield better in a real-life manufacturing process is called design for manufacturability, or DFM. And then, of course, the other obvious way is to reduce the defect density, D0, in our equation. This requires inspection, review, classification, and analysis of the data. Let's look at those very, very quickly. Defects are classified based on size and type. We want to know how big it is, because that affects our yield estimates. But we also want to know what kind of type, what kind of defect it is, because that helps us understand where the defect came from and what we have to do to eliminate the source of those defects. First, though, you have to find the defects. We do this with wafer inspection. Often, almost always, it's an optical method. We shine light on a wafer and look for scattering or differences in the images of the wafers. If we have a wafer with 100 die, we might do a die-to-die inspection where we look at an image of one die, compare it to the image of the die next to it, and look for differences. Any difference is a defect because every die should be identical. We sometimes use electron beam microscopes to do this wafer inspection, but they tend to be very slow and expensive. So we try to find our defects using optical inspection tools. Then we have to review the defects. Here, an optical inspection tool doesn't have in general, doesn't have the resolution required. So while for bigger defects or older defects we can use an optical review, today most of our defects are classified using a scanning electron microscope. Once we classify the defect, then we can do analysis on the defects. Where are the defects landing? When do they occur in the process? What's the likely source? And can we go and find that source and eliminate it? Here's some examples of the kind of equipment that you can use. These happen to all be from KLA-Tencor. I got these images from their website. I used to work for KLA-Tencor, so I'm going to stick to their pictures in my presentation, but of course there are other vendors of these kinds of tools as well. We have bare wafer inspection tools. This is where we take a blank wafer and inspect it for defects. We do that not only at the very beginning of the process, but we do that as a way of monitoring the equipment. We'll take a bare wafer, we'll measure the defects on it, then we'll send it through a process tool, like a deposition tool. And then we'll measure it again and see if there are more defects. We call those adders. Or fewer defects. Sometimes defects get removed. It's kind of a self-cleaning process for some kinds of processes. And we can see defects come and go. Bare wafer inspection is very useful for characterizing equipment sources of defects. But we also need to inspect pattern wafers. After we start patterning, go through the process, all along the way we need to keep inspecting our wafers. And finally, once we find a defect, the exact location of that defect is through software passed to a defect review station. And in that defect review station, we'll, using an electron microscope, look in high resolution at that defect. Take a picture of it, classify it maybe automatically with some auto classification software, and do some analysis. Some of the issues involved in defect detection are things like sensitivity versus throughput. Sensitivity is what's the likelihood that I'm going to find a defect. And throughput, of course, is how fast I can move wafers through the tool. We want high throughput for low cost. But often, to get high sensitivity, especially for small defects, I end up having to use tool settings that lower the throughput. We also have this trade-off between the false defect rate and the missed defect rate. I don't want to miss any critical defects that are on the wafer. But if I set my sensitivity settings to be very, very sensitive so that I catch every defect that might possibly be on the wafer, chances are I'm going to have a high false defect rate. I'm going to find defects, I'll go review them, and when I review them, I don't see anything. False defect rates have to do with noise in the inspection equipment. And every instrument has noise. So we have this trade-off between the false positives and missed defects. There's lots of types of defects. Once we characterize the defects, we will categorize them, put them into bins. We'll count them. We'll find out the numbers of defects that come from this source or that source, and this categorization of defect types will help us identify the sources of defects and eliminate those sources. Here's some examples of 5 kinds of defects that might occur during CMP, and depending on what defect you find, you might identify the source as being some, for example, residual slurry. That's a pretty clear example. We didn't rinse the slurry off of the wafer well enough, etc. So, what have we learned in our very, very brief discussion of an extremely important topic, yield and defects? What are the 2 major types of die yield loss? What are the 2 parameters in our simple defect yield model? And finally, what is DFM? Next time, we're going to continue a discussion of semiconductor manufacturing, and we'll talk about something called SPC, Statistical Process Control, and a metric called process capability. How well is our overall manufacturing process working? Till then.